Hello, everyone. This is Zhou from the University of Virginia. I'm going to present our work on robustness testing of data and knowledge-driven anomaly detection in cyclophysical systems. Machine learning models are increasingly used for anomaly detection due to their easy implementation, high accuracy in predicting and seeing data that shares similar features with training data, and powerful capability in approximating complex dynamic models of control system. However, their performance heavily relies on the quality and quantity of the training data and may suffer from degradation in accuracy due to input perturbations. Also, they lack transparency and interpretability. Although the robustness of our machine learning models against adversarial perturbations has been widely studied for computer vision and speech recognition applications, less attention has been paid to robustness of anomaly detection models against perturbations on multivariate time series data, or possible methods to improve the robustness of safety monitoring. So in this paper, we would like to explore two research questions. First, how robust are the state-of-the-art machine learning safety monitors against accidental and malicious input perturbations? And does the integration of domain knowledge help with improving the robustness of the machine learning models? We tested the robustness of machine learning-based anomaly detection models against both accidental and malicious perturbations on multivariate time series input using a Gaussian-based noise model or adopting a fast gradient sign method. We integrate the domain knowledge with machine learning models using a semantic loss function. We evaluate the robustness of machine learning-based safety monitors for two artificial pancreas systems with different controllers and patient glucose simulators in comparison to two state-of-the-art baseline monitors. This figure shows the typical control structure of a cyclophysical system. There's often a time gap between the activation of a fault until the propagation of the unsafe control action to the physical layer, resulting in a safety hazard. So the design safety monitor can be attached to the control system as a wrapper with only access to the input and output data to inform whether a control action issued by the controller will be safe or unsafe and prevent it before it is delivered to the physical layer if it is unsafe to prevent a safety hazard. The figure in the left shows an example about how a safety monitor works. As we can see in the middle of the figure, the black line indicates a high insulin is issued by the controller and delivered to the virtual patient at about 400 minutes, and the hazard happened as shown in the orange bar in the bottom figure. So the safety monitor, as we can see in the bottom figure with the green bar, can generate the safety alerts in time before the occurrence of the hazard. This figure shows the overall framework. The integrated domain knowledge was extracted by generating the safety context of the application using a control theoretic hazard analysis method, which defines whether a control action issued under a specific system context will result in any hazard. To generate the safety context specification, we define the actions and hazards, transformation or partition of the measurements, and then identifying whether a combination of the control action as well as the partition of the measurements will lead to any hazard. For example, in artificial pancreas system, actions can be defined as complications from hypoglycemia or hypoglycemia, which include severe patient injuries or even death. Possible hazards that might result in these actions include too much insulin is infused or too little insulin is infused. An example generated context table is shown in the table. For example, the last law specifies that under the system context, that the blood glucose value, which is the BG, is less than the target value and keep decreasing while the insulin on board is increasing. A keep insulin command is unsafe if issued by the controller and may lead to low blood glucose hazard. We model the task of anomaly detection as a conditional event as shown in the first equation. So given a sequence of contraction UT under the system state sequence XD, the machine learning model outputs a binary value YT that classifies the contraction UT to be safe or unsafe. The domain knowledge is integrated into the machine learning model using a Gaussian loss function as shown in the second equation. So we add the Gaussian loss function as an regularization item to the existing loss, which indicates whether any of the STL formulas are satisfied over the measurement window. This forces the satisfaction of the safety properties by penalizing the machine learning models if the outputs of the machine learning model is different from the STL formulas. And this loss function will also help with the interpretability of the machine learning-based monitors. For robustness testing, we use a Gaussian noise model to simulate the environment noise, as it approximates white noise well in the environment and can be entirely described by second-order statistics. To generate adversarial examples, we adopt a faster gradient sign method that adds a small perturbation to the input according to the model gradient. An example is shown in the figure. As we can see, the model output changes from the unsafe contraction to safe contraction with a very high possibility after adding the perturbation to the input. However, this method requires full access to the target model, which might not be possible in some situations. Therefore, we also designed a black box attack with limited access to the ML model. We generate the perturbations from a substitute model and expect it will work on the target model. One of the case studies we are interested in is artificial pancreas system, as we can see in the figure, which has been studied for years. They are closed-loop systems that constantly measure blood glucose value and issue insulin and glucagon in the right amount at the right time. We integrate 2 glucose simulators in the simulation, which include 40 patients in total. We collect training data and testing data from over 800 simulations for each patient. We use prediction accuracy to evaluate the performance of each machine learning-based models in detecting anomalies, including precision, record, accuracy, and F1 score, which are measured using a sample level with tolerance window metric as shown in the figure. Unlike the traditional point-wise method, this metric considers a lot within a tolerance window before the occurrence of a hazard to be true positive, due to the requirement of early prediction of anomalies. We also use a prediction robustness error metric as shown in the equation, which measures the percentage of samples that fail to keep the same prediction after adding perturbations, with smaller value representing more robust and better. We first evaluate the performance of each ML monitor, as well as a rule-based one, which is developed purely based on domain knowledge in detecting anomalies without any perturbation. We see that the MLP safety monitor trained with Gaussian loss function achieved a higher F1 score than baseline MLP monitors, as well as the rule-based safety monitors. This indicates the advantage of combining domain knowledge and the data-driven techniques. Although the LSTM models trained with the Gaussian loss function did not improve the F1 score of baseline LSTM models, they achieved comparable accuracy and improved their interpretability. Here we show an example of the decision boundaries of baseline MLP safety monitor and the custom MLP safety monitor trained with custom loss function. We see that the customized MLP monitor detects more anomalies in the right figure. After adding the Gaussian noise, both ML models' performance decreases, while LSTM model has a larger drop, indicating it is less robust against small input perturbations. We also observe that the F1 score of the MLP monitor increases with the rise levels of added noise in UVA simulator. This might be because the large numbers of new alerts generated due to noisy input that increase the initially low recall of the baseline MLP monitor and also resulted in decreased precision as shown in the figure. In both simulators, the monitors trained with custom loss function reduced the performance drop and kept the F1 score high with noisy input data. This demonstrates the advantage of the integrated domain knowledge in overcoming disturbance in input data, as well as the robustness and the generalizability in maintaining stable performance for anomaly detection with different machine learning models and different controllers. We observe similar performance degradation on the white box fast gradient sign method attacks, indicating these ML models' incapability to keep stable performance under adversary attacks, as well as the efficiency of white box FGSM attacks in fooling machine learning models for anomaly detection. Example adversarial samples are shown in the left figures. Similarly, the customized ML models achieve better performance and robustness, as we can see in the right figure. We further evaluate each ML monitor's robustness against small input perturbations using prediction robustness error metric. We see that baseline ML monitors are more vulnerable to FGSM attacks with larger robustness error, as we can see in the figure, than simulated environments in the input data. Also, the baseline LSTM monitor is more sensitive to both FGSM attack and the Gaussian noise, due to the disturbance on both their current sensor data and short memory. Almost all the machine learning models have more significant robustness error against FGSM attacks in the UVA simulator than in the Gaussian simulator, which might result from different patient profiles. We also observe that the ML models customized with the semantic loss function have the least robustness error, which further attests the advantage of the integrating domain knowledge in keeping the model predictions stable and robust. Finally, we evaluate the robustness of each ML monitor against black box attacks generated using a substitute MLP model. We see that the baseline LSTM model kept the robustness error below 0.23, which is 2 times less than the robustness error against white box attacks. Also, the inclusion of custom loss function reduced the robustness error. To summarize, robustness testing of ML monitors showed large reductions in model performance, despite the models performing very well on noise-free data. Also, the incorporation of domain knowledge significantly improved robustness when compared with baseline monitors, without sacrificing accuracy and transparency. Future work will focus on a more comprehensive investigation of robustness testing and defense strategies for machine learning anomaly detection models in CPS. Thank you.